The nature of light and the photoelectric effect are going to be the topics in this lesson, and we're going to start by talking about the wave-particle duality of light. Turns out light has both a wave-like nature and a particle-like nature. It simultaneously displays wave-like characteristics and particle-like characteristics, and we'll take a look at that. We'll take a look at wave-like characteristics like the wavelength and the frequency, and then we'll look at particle-like characteristics like the energy of a photon. And then we'll take a look at the electromagnetic spectrum and what you need to know about that, and then finally we'll polish this lesson off talking about the photoelectric effect, where electrons can be ejected from a metal by a photon of light. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. In addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. Now, this lesson's part of my new general chemistry playlist. I'm releasing these lessons several a week throughout the school year, so if you want to be notified every time I post a new lesson, subscribe to the channel, click the bell notification. So let's get into this. If we take a look first at the wave-like nature of light, and so it turns out that light, again, behaves like a wave in certain characteristics, and it has a characteristic wavelength and a frequency. And so if we take a look at a wave here, you can kind of look at a wavelength here as being the distance from any point to the analogous point in the wave. And here I just went like midpoint to midpoint, but you could have gone like peak to peak or trough to trough. Any of those would get you a wavelength, and we use the symbol lambda to represent that wavelength. Now, it turns out there's also a frequency associated with light, and a frequency is nothing more than how frequently the wavelengths pass through a given point in space. And we use the Greek letter nu here to represent frequency, and it's going to have units of per second, which we often refer to as hertz. And it's just the number of wavelengths passing through a given point in space per second. So if it's 5 per second, we might say 5 hertz is the frequency in this case. And it turns out there's a mathematical relationship that you definitely have to know here between wavelength and frequency. And it turns out for any wave, the wavelength of that wave times its frequency is going to equal the speed of the wave, which in the case of light equals the speed of light, c here. And the speed of light in a vacuum is 3.0 times 10 to the 8th meters per second, and the speed of light through air is nearly exactly the same number, but through different mediums like passing through water or glass, it does have a different speed, and you'll study that more in a physics class, but we're always going to be using the speed of light in a vacuum, which again is pretty much the same thing as the speed of light in air. And this 3.0 times 10 to the 8th meters per second is fast. So if you look at that speed of light, it's like 186,000 miles per second. You can go around the equator of the Earth 7 times in a second. You can go to the moon and back in 3 seconds. You can get to the sun in a little less than 8 minutes. The speed of light is fast. And once again, your wavelength times your frequency equals that speed of light. And so this lovely equation here only has 2 variables because c here is a constant. And the 2 variables are wavelength and frequency. If you know one, you can calculate the other. And we'll do just that here in a little bit. But the big thing here is that you should realize that these are also inversely proportional. If you get a longer wavelength, then you're going to have a smaller frequency so that they multiply out to give the same constant speed of light. Okay, so that's the wave-like behavior of light, dealing with wavelength and frequency. But light sometimes also behaves more like a particle when we look at it under certain conditions. And we call those light particles, or I like to call them light bullets, we call them photons. And it turns out that the energy of a photon is proportional to its frequency. You double that frequency, it doubles the energy. And it turns out this proportionality constant, it's a constant here, h, is called Planck's constant, and it's 6.626 times 10 to the negative 34 joule seconds. And one thing you should know here, so these 2 constants, if you're going to be on the hook for either of these constants, it's more likely to be the speed of light, but oftentimes we'll give students both of these constants, we'll make them available to them, especially Planck's constant, not usually something most courses or instructors are going to make you memorize, so just an FYI. All right, this last equation here also only has 2 variables then, because again, h is a constant. The only variables are the energy of the photon and the frequency. If I give you the frequency, you can calculate the energy of a photon. If I give you the energy of a photon, you can calculate the frequency. But again, the big thing you should realize is that they're directly proportional. Double the frequency, double the energy. Now, if you were sitting in the room with me right now is the time where I would ask you, hey, what's new? So, and the correct answer here to what's new is c over lambda. So again, this letter right here is not the letter V, it is the Greek letter nu. It's kind of a funky looking slanted V, but it's the Greek letter nu. And so when I say what's new, I'm expecting you to actually solve for it in that first equation. So, and you'd see that nu equals c over lambda. And then we're going to substitute that in right there into this second equation for the energy of a photon. and we can see that we can write the energy of a photon in terms of the wavelength instead. All right, so what's new? Only proper answer in this chapter is c over lambda. And so the energy of a photon in this case is equal to hc over lambda. H and c are still constants. And so there's only two variables here. And if you know the energy of a photon, you can solve for the wavelength. If you know the wavelength, you can solve for the energy of a photon. But here you can see that they're actually inversely proportional. If you double this wavelength, then you're going to cut the energy of the photon in half and vice versa. So they're inversely proportional. As one goes up, the other goes down. All right, so now that we've understand some relationships here, before we do any math though, we just want to take a look at the broader electromagnetic spectrum. So it turns out that the rods and cones in your eyeballs only can detect a very narrow range of the spectrum that we call visible light. So it turns out the entire electromagnetic spectrum, we can refer to all of it as light, or we could just refer to the visible part of it as light as humans. That's what we can detect. But there are certain snakes that can detect infrared radiation. Or, so if you have seen Predator with Arnold Schwarzenegger, so the predators can also detect this as well. That's kind of like your heat signatures. So my camera that's filming this actually has an IR detector as well, and I could film in the dark and turn on the IR light and things of this sort. But normally your eyeballs though aren't going to detect infrared or anything else outside of this visible range. And so, but the broader electromagnetic spectrum, you should know the relative positions of all the different types here. And we want to start by talking about the energy of electromagnetic radiation. And energy increases going this way. And what you'll generally see, with one major exception though, is that the rays get more harmful to you as a human as they rise in energy. And so gamma rays here are the highest energy electromagnetic radiation, whereas radio waves would be the lowest energy. And so first off, you just got to memorize this. And you might just, you got to know these relative positions. And you might be given 5 of these and just asked to rank them in order in a multiple choice question, or just which one's the highest or which one's the lowest energy. So in that sort of thing. So you definitely got to know this order. And one way to look at that again is just memorizing what's more harmful. So these gamma rays are what you find most notably in nuclear radiation. Now, not all nuclear radiation is gamma rays, but gamma rays are pretty often present in nuclear radiation, and they are super harmful to you and will kill you very quickly. So next on the list is X-rays. So and X-rays will kill you, but not nearly as fast as gamma rays. But notice when you go to the dentist, they're going to put a lead, vest over you, and then they're going to leave the room when they give you an X-ray because they don't want to be around while they're zapping you. So, but it'll probably give you cancer very slowly if you're exposed to quite a bit of X-rays, not nearly as fast as gamma rays there. And next on the list is ultraviolet and ultraviolet light. And I live here in Arizona, and we get lots of ultraviolet light. And if you're as light-skinned as me, you know that you're going to have problems if you get way too much ultraviolet light, especially. But all of us will eventually have some problems here, melanoma and things of this sort. But again, probably not going to kill you near as fast as either X-rays or gamma rays. So, and then finally we get to visible, and then less energy than visible is infrared. So, and then there's microwaves. You might be like, Chad, you told me it gets more harmful, and I don't recommend you getting a microwave. So, and that's true. So it turns out microwaves have just the right amount of energy to cause water molecules to spin, to rotate, it turns out. And that's how they heat up your food. When they rotate, they cause friction and things of this sort. And so that's the deal with microwaves. So they're kind of special, but they're still lower energy than even infrared waves here. And then finally, lowest energy on the electromagnetic spectrum here is radio waves. Okay, now this looks at it in terms of energy, but you should also be able to look at it in terms of frequency and wavelength. And we said here we could see that the frequency and the energy were directly proportional. You double one, it doubles the other. And so if energy is increasing going up this list, then so is frequency. And so instead of talking about the energy, you might get a question that talks about the frequencies instead. And again, you might just get 5 of these listed in a multiple choice question and said, which is the highest or lowest frequency, one of those two. Now, in terms of wavelength, though, we saw that both wavelength and frequency were inversely proportional, but we saw that the energy of a photon and wavelength were inversely proportional as well. And so you should know that in terms of wavelength, though, it goes the opposite direction. And so even though gamma rays have the highest energy and the highest frequency, they have the shortest wavelengths. And even though radio waves have the lowest energy and the lowest frequencies, they have the longest wavelengths. So you should definitely know these relative positions. You might also need to know, breaking out this visible spectrum here. So if we kind of divide it up here just a little bit, So what's nice is if you look at ultraviolet and infrared, so the visible spectrum is composed of the different colors. And it turns out the different colors give you the different frequencies and wavelengths. And it turns out the highest energy visible light right below ultraviolet is violet. And it turns out the lowest energy visible light right above infrared is red. And it turns out if you want to break out those colors, and it's the colors of a rainbow, in between we've got a mnemonic for that is Roy G. Biv. So, and that's red, orange, yellow, green, blue, indigo, violet, and real common mnemonic there, and probably worth knowing these guys as well. And for some of you, your professor may even want you to know wavelengths here. So red light is about 700 nanometers, and violet light at the other end of the spectrum is right around 400 nanometers as well. So that's your visible spectrum. So if you've got a longer wavelength than 700 nanometers, you might be infrared, microwaves, or radio waves. If you've got a shorter wavelength than 400 nanometers, you might be ultraviolet, X-rays, or gamma rays, depending on just how short it is. So, but knowing these relative positions in terms of energy, frequency, and wavelength, something you need to memorize and make some flashcards on or something along those lines. All right, so now let's get into the math of this lesson. So, and the math here is just a little bit of a pain in the butt, but not terrible. So, but in all three of these expressions right here, there are only three variables. There is wavelength, there is frequency, and there is energy of a photon. And it turns out they are mathematically interdependent. If you know any one of the three, you can calculate the other two. So, and it doesn't matter which of the three you actually know. Any of those three will allow you to calculate the other two. If you know the wavelength, you could use this first equation to calculate the frequency. If you know that wavelength, you could use this last equation to calculate the energy of a photon. If you know the frequency, you could use this first equation to calculate the wavelength. And again, if you know that frequency, you could use the second equation to calculate the energy of a photon. So you just got to pick the right relationship to calculate the one that you want. And so in this case, I'm going to give you one of these. I'm going to say that, hey, we've got some light, and this light has a wavelength of 400 nanometers. And if I give you that wavelength, the question then is, well, get me the frequency and get me the energy of a photon. So, and in this case, let's get that frequency first. And if we want that frequency, well, it's the first equation that compares the wavelength to the frequency. So that's the one we want to use. But if we want to solve for that frequency, again, what's new? It's equal to c over lambda. And so we'll take c, 3.0 times 10 to the 8th meters per second. And now we're going to divide by lambda, but we have to be careful here. So frequencies, you might recall, have units of seconds to the -1, or 1 over seconds, which are called hertz per seconds, which means my wavelength here is going to need to cancel out the meters part so that the units are going to come out in per seconds, hertz. Which means I got to put this in meters, but it wasn't given in meters, it was given in nanometers, which is pretty common for visible wavelengths. And so the first thing we have to do is convert this into meters. So, and it turns out 1 nanometer is 10 to the -9 meters, back from your metric conversions back in the first chapter. And so in this case, I don't even have to put this in proper scientific notation. I can just put it in just like this and make it 400 times 10 to the -9 meters. Not proper scientific notation, but I'm only putting this into my calculator anyways. It's not going to get reported on anything regardless. Cool, and from here it's calculator plug and chug, but you could possibly do this on your own, because 3 divided by 4, if I wrote this in proper scientific notation, it'd be 4 times 10 to the -7 meters. And in that case, 3 over 4 is 3/4 or 0.75. And then you could work on the powers of 10 and get it in proper scientific notation. And what you'd find here is that it would equal 7.5 times 10 to the 14th seconds to the -1, or per seconds, or very commonly going to be written as hertz. Okay, so now we found the frequency. And we started out with that wavelength. Now we've got to get the energy of a photon. We have 2 different ways to do it. So, and had we wanted to get it directly from the beginning, we might have used this last expression. So, but the truth is, it looks like a little easier calculation now that we know the frequency to use this second expression instead that relates the energy of a photon to the frequency. And that's the route I'm going to go. And so h times the frequency, h again is Planck's constant, 6.626 times 10 to the -34 joule seconds, and then times the frequency, 7.5 times 10 to the 14th seconds to the minus 1. And we can see here again that those seconds and seconds to the minus 1 will cancel, and we're left with an answer in joules. And this one I will resort to my calculator for. 6.626 e to the negative 34 times 7.5 e to the 14th gives us 4.97 times 10 to the negative 19. And again, that's in units of joules. Now, this is a super, super tiny amount of energy, like super, super small number, and something that doesn't mean a whole lot to you or I. You know, if we talked about, how much energy do you need to run your house in a month or something like that, it's way more than this. It's way more than 1 trillion times this. So this is so small. Now, if you're an electron, though, this is actually a fairly significant amount of energy. And it turns out that electrons often either absorb or emit the energy of a photon of light and stuff like this. So it turns out that, there might be a more convenient set of units when you're talking about electrons, and we call them electron volts. And so we're going to rewrite this in terms of electron volts. Now, not all of you will be on the hook for this, so this is kind of something that's going to be for some of you, but it turns out we can take this 4.97 times 10 to the negative 19 joules and convert joules to electron volts, and it turns out that 1 electron volt is roughly 1.6 times 10 to the negative 19 joules. And if they were giving you more sig figs, it'd be like 1.602 times 10 to the negative 19 joules. And so if we take 4.97 times 10 to the negative 19 divided by 1.6 e to the negative 19, we're going to get roughly 3.1 electron volts. Cool, so here's the energy of a photon here of this violet light in joules, and here's the energy in electron volts. And we can see why it might be easier to kind of talk about the energy in electron volts. If I said, hey, this is the energy of 1 photon of this violet light, this blue light, violet, whatever I said. And so in this case, my question would be, well, what would be the energy of 2 photons? Well, doubling this number is easier than doubling this number in all likelihood. And so in this case, we'd just be like, well, it's 6.2 electron volts. What would be the energy of 3 photons? Well, it would be 9.3 electron volts. We could do that in our head. Now, one thing to note, this equation always gives you the energy of 1 photon. So, and again, they could ask you the energy of 2 or 3 or something like that, but most likely they're going to ask you the energy in joules per mole. And so if they're asking for an energy in joules per mole, well, that's the energy of an entire mole of photons. And so with 2 photons, we multiplied the energy by 2. With 3 photons, we multiplied the energy by 3. With a mole of photons, you're going to multiply by Avogadro's number. And so you'd take 4.97 times 10 to the negative 19. 4.97 e to the negative 19 times 6.02 e to the 23rd, and you'd get 299,000 roughly. We'll round it right there. 299,000 rounded to 3 sig figs, and that is going to be in joules per mole. And that's something that also shows up quite commonly for talking about the energy of photons. So 3 different energies for this photon that are all equivalent in one way, shape, or form. These 2 in 2 different units for 1 photon. This one, the energy of an entire mole of photons. So now we're going to talk about the photoelectric effect, and the photoelectric effect was one of the early evidences for quantum mechanics being true. And at the heart of quantum mechanics is the quantization of energy. And in this case, we're going to look at the quantization of the energy of an electron as well as the quantization of the energy of a photon of light. Now, it turns out quantization shouldn't be a scary word, but it is, and quantum mechanics is scary, but it all lies around the term quantity in this case. And it just says that energy can only have specific quantities, like the energy of an electron or the energy of a photon. They can only have specific quantities, and this is more bizarre than it would seem like on the surface. But let's say I had a car, and I'm going to say it's a quantum car, and it had a quantized velocity, a quantized speed. And so my quantum car can only go certain speeds. And in first gear, it goes 10 miles an hour, and then I shift it into second gear, and it goes 20 miles an hour. And third gear, it goes 30, and in fourth gear, it goes 60, just jumps to 60. And so it turns out those are the only speeds my car is allowed to do. In first gear, 10, in second gear, 20, in third gear, 30, and in fourth gear, 60. and it doesn't do any other speeds. You will never, ever, ever find my car doing any other speed, this quantum car. And so when I shift from like third gear and I'm doing 30 miles an hour and I shift to fourth gear and go to 60 miles an hour, it's not like it speeds up from 30, 35, 40, 45, 50, 55, 60 and gets up to 60. It instantaneously jumps from 30 to 60. Doesn't pass through any of the velocities in between. It just instantaneously goes to the new speed. So, and nothing in the macro world works like this. And so only certain quantities being possible is just not something we're used to seeing in the macro world. But in the micro or really, atomic world here, it's totally the way things work. And I guess subatomic world would be a better way of putting it since we're talking about electrons. And in this case, it turns out that, commonly electrons in atoms or electrons as part of a metal, it turns out, this is a metal here we're going to be talking about, do have a certain amount of energy associated with them, and you can knock one of these electrons out of this metal if you hit it with light. But that light has to have the right amount of energy, at least to a minimum, as well. And this was a little bit bizarre. So it turns out that we just learned that the photon of light has different energies based on its different frequencies or wavelengths, which again our eyes interpret as different colors and stuff like this. But classically, that's not what the scientists thought. Scientists thought that the energy of light was related to its intensity of the beam. So you could have like a really faint red light, or you could have a really bright red light. And so now we've learned that as long as it's the same shade of red, the energy of each individual photon doesn't change. So you might have more of those photons is what the bright light actually means, versus the faint light would mean less of those photons, but every one of those photons would have exactly the same amount of energy. Whereas if you ramp that up to say blue light, all of a sudden now, so the blue light, every single photon in the blue stream of light is going to have more energy. And you could still have a more intense blue light or a less intense blue light, which still just is going to regulate how many blue photons you have. But the blue inherently has a higher energy associated with it. And this was not what they expected. So let's say we got a metal here, and it turns out metal has what's called a work function. And this work function is represented by the Greek letter phi here, and it describes the minimum amount of energy it would take for a photon to eject an electron from that metal. And so let's say we've got here the, whatever this metal is, and let's just say we got a work function of 2 electron volts. And so what this means is, let's say I start hitting this metal with photons of just 1 electron volt. And so if I hit it with a photon of 1 electron volts, no electrons are going to get ejected because for this particular metal, it's going to take at least 2 electron volts. And it turns out all the different metals, copper, iron, silver, they're all different in their work functions. Some hold on to their electrons more tightly and have higher work functions. Some hold on to them more loosely and have lower work functions. But they're all different. So for this particular metal, I'm just saying it's 2 electron volts. Okay. It turns out every photon has the opportunity to eject 1 electron. So it's a 1-to-1 ratio. 1 photon, 1 electron. If you want to eject 2 electrons, you're going to need at least 2 photons. But the key is the photons have to have at least the minimum amount of energy, the work function amount of energy. And so if, again, my photons only have 1 electron volt, it doesn't matter how many of these photons I shoot at this metal, they're not going to eject any electrons. So I can crank this beam of light way up and make it super intense. But again, if every photon in that beam of light is 1 electron volt, no electrons are going to get ejected. But let's say instead, I change the color of the light, and I change the color of the light to say maybe be violet, which we saw was right around 3 electron volts. And so now if I start hitting it with light that's 3 electron volts, that's more than the threshold, more than the work function, and now electrons are going to start getting ejected. And every photon that hits the metal can eject an electron from the surface. So if I hit it with 5 of these blue or violet photons, so then I could eject 5 electrons potentially, as is the case. Now there's more to it than this though. It turns out that we've got some math associated with the photoelectric effect, and the math just tells us that this electron that gets ejected out, it has the potential to be moving faster and faster and faster if you hit it with higher and higher energy light. And so if we just break down what this equation really means, is it says that any excess energy you hit this electron with, it gets to keep it as kinetic energy. It's going to come off faster. Kinetic energy is the energy of motion. And so in this case, if I hit it with 3 electron volt light, that's our energy of our photon, well, and then we subtract off the work function, which was the minimum, we'll find out that the kinetic energy the electron gets to keep is 1 electron volt. Now, if instead of hitting it with 3 electron volt light, what if I hit it with 5 electron volt light? Well, again, the first 2 electron volts is just what it takes to get it off the metal. Anything else the electron gets to keep. And so, again, if I hit it with 5 electron volt photons of light, the electron's going to come off, in this case, with 3 electron volts of kinetic energy. So, and it would just be 5 minus the 2. The extra 3 electron volts would have been excess in that case. So jack it up to 5, and now we're going to get 3 electron volts for the kinetic energy of the electron. Now, the truth is this is actually the maximum amount of kinetic energy the electron can have, but we usually just kind of gloss over that in chemistry. In a physics class, you might study that in a little more detail. So we'll just call it the kinetic energy of the electron, even though it's really just the maximum amount of kinetic energy of that electron. Cool. But this is the photoelectric effect. It told us that the electrons in the metal have certain energies associated with them, that their energies are quantized, which again was fairly revolutionary. Not even fairly, it was very revolutionary at the time. So a couple of the guys that's, really had a good handle on it at the time, one of them said, if quantum mechanics makes sense to you, then I'm positive you don't understand it. It is just bizarre and it doesn't make a lot of sense. So, but it does line up with a lot of the experimental evidence we have. So, and it's one of the most sure theories we have out there, quantum mechanics, that the energy of an electron is indeed quantized and the energy of these photons of light is quantized as well. Now, if you found this lesson helpful, hit that thumbs up button. And quick thing, this is my new camera. So if you guys have been watching some of my lessons, leave me a comment. Let me know. Can you tell the difference between the old camera and the new camera? Can you see like the wrinkle lines in my forehead a little better? But more importantly, does the writing on the board look a little better and stuff as well? So let me know. And if you like the new camera, fantastic. And if you hate it, let me know. I had to actually adjust the lighting. The camera was so much better than my old one that my lighting was not, was like too good or not good enough or something along those lines. So, but let me know what you think about the new camera. And if you are looking for general chemistry practice, if you're looking for final exam rapid reviews, practice final exams, check out my general chemistry master course. I'll leave a link in the description. A free trial is available. Happy studying.